Okay, so hello everyone. Welcome back to the course. I hope you all had a good weekend. Yeah, it always seems weird on a Monday. It's like it's been forever since the last lecture. Anyway, good thing everyone's back, even though I can't see you in person. So let's see. So where were we last week? So we were, pretty much done parsing. We looked at LR1 parsing, and the idea was we wanted to build a better parsing NFA and DFA that takes advantage of the fact that we can run that DFA not only on the parsing stack, but also on the next symbol of the input. And I ended off saying that this DFA can be quite big, and on the order of, say, a megabyte of memory to store it, and that the most popular parsing algorithm is not LR1 but LALR1. And it has most of the benefits of LR1, except it allows you to parse with a much smaller DFA. All right, and so today I want to tell you some details about LALR1. It is something where the theory is hard to understand, hard to make precise. So I don't want to dwell on it too much, but I want you to have a sense of what it is, since it is so popular, right? And you're likely to see it a lot in terms of parser generators and parsers. And I just one other thing to repeat is that the actual parsing algorithm itself is the same for LR1 or LALR1 or SLR1. It's only the parse table, the implementation of that reduce function that tells you what to do at each step that differs. Okay, so again, if in your assignment, if you implement one of them, well then you can use your implementation with any of these DFAs. Okay, so I left off at the end of the last lecture saying that the idea for LALR1 parsing is that we want to use the LR0 DFA, which we know is smaller. But with SLR1 parsing, we also use the LR0 DFA, and we use the follow sets to help us. And then I showed you an example of a grammar where that didn't work. And so, and the reason was that there's only one follow set for each non-terminal symbol in the grammar, and you have to use that one follow set globally. So in every place in the grammar where that follow set appears. So the idea here is that for every DFA state, we're going to be allowed to compute a separate follow set. So every DFA state can have a different follow set, and that way, when a non-terminal is used in different places in the grammar, those different places can have customized different follow sets. Okay, so what are we going to do here? So we want to use the LR0 DFA. We want to compute these follow sets. And how are we going to compute them? Well, we're going to compute them from the LR1 DFA. Okay, so I'm going to start with a definition. And I'm going to say if Q is a state of the LR1 DFA state, okay, then we're going to say that the core of Q is just that LR1 DFA state, but with all the look-ahead symbols removed. So I'm going to say that the core of Q is going to have is a set, and it's going to have A goes to alpha dot beta. So a production rule with a dot in it such that A goes to alpha dot beta, and some look ahead symbol is in Q. Okay, all right, and I've already failed. I wanted to keep the second board free for the example, but oh well. Okay, so what does this mean? So remember that our DFA states, each DFA state is like a set of NFA states. So this Q is a set of NFA states, and the LR1 NFA states have a production rule with a dot in it, and they have a look ahead symbol. And so all we're doing with the core is we're saying we're going to take each of those NFA states and throw away the look ahead symbol, and then we'll have a set of those production rules with the dots in them. Okay, so you can think of the core as a way to convert an LR1 DFA state into an LR0 DFA state, and in fact, if I was to take the LR1 DFA and replace each state with its core, and kind of match up the transitions. So the idea is I want to merge all the LR1 DFA states that have the same core into a single state, right? Same core means having the same production rules with the same position of the dot, but possibly different look ahead symbols. So I merge all of those, and I get an LR0 state. And if I do that for the entire LR1 DFA, I'm going to get the LR0 DFA out of it. Okay, so if we replace every state with its core, we get the LR0 DFA. And so now, maybe it becomes obvious how we're going to compute a follow set for every DFA state. Well, we're going to take the look ahead symbols in all of the LR1 states that have that LR0 state as their core, and we're going to put all those look ahead symbols in a set. So the main idea is follow set set of a LR0 DFA state contains the look ahead symbols from the corresponding LR1 states. Okay. All right. So once again, we take all the LR1 states that have the same core, and for each, so that means they have the same production rules with the same location of the dot, and for each one of these LR0 items, so or you can call them the LR0 NFA states, we take the union of or we make a set with all the look ahead symbols from all the LR1 states. Okay. All right, and I think I might as well use the middle board now. Right? So let's turn this into an algorithm, and let's say where the input to our algorithm is going to be the LR0 DFA, and so we'll call that M. So LR0 DFA, and M prime is going to be the LR1 DFA. Okay, so we're going to take the two DFAs as input to this algorithm that constructs the LALR DFA. And so now for each state of M, so state Q of M, so for each state of my LR0 DFA, I want to look, I want to find the compute a follow set. So I'm going to go over all the items. So all the elements of Q. A goes to alpha dot beta, so a rule with a dot in it. So for each element of Q, okay, and now we're going to compute that look-ahead set. So that follow set. Okay, so the follow set is for each of these items, so each of these production rules. So the follow set is, okay, and I'm going to do a set A such that, and so, such that what? So such that Q, so Q prime is a state of M prime, whose core is Q. So Q is the core of Q prime. Okay, so we're going to look in the LR1 DFA for all the states that whose core is Q, and A goes to alpha dot beta with look ahead little a is in Q prime. Okay, so we're looking through the LR1 DFA. We're finding all the states Q prime that have Q as their core. Then we're finding that item, that production rule in each of those LR1 states. And we're taking its look ahead, that's a single symbol, but we're collecting all those look ahead symbols up in a set. And that set then becomes the follow set for that production rule, or sorry, for that item in our LR0 DFA. Okay, so in the LR1 DFA, for each of these items, you have one follow symbol. In the LALR DFA, it looks like, or the syntax, the shape of a state is similar. So you have a set of production rules with dots in them, but for each production rule, you're going to have a set, a follow set of symbols. So not just a single look ahead symbol. Okay, so this is the general stuff, and I think to really get it, I need to do an example. So I'm going to do an example. But just before I do that, any questions on the general idea? Okay, and now that I have the general algorithm down here, I want to try to explain, why this is messy and tricky to understand. And sort of the tricky part is that you're trying to come up with a follow set for one of these items, right? One of these production rules with a dot in it. And but the way you get that follow set is not by looking at NFA states, right? An NFA state, looks like this, like it has that rule in it, and it has a look-ahead set. But you're actually looking at all the DFA states in the LR1 DFA. And so the follow set that you're going to get is influenced by the groupings of the NFA, the LR1 NFA states into DFA states, right? And it's pretty hard to predict how the various NFA states are going to get grouped together into DFA states because that depends on different paths through the NFA for the same input string, right? So you kind of, to really predict what the follow sets here are going to end up looking like and what the LALR DFA is going to look like, you really have to not only have the LR1 NFA in your head, but actually do that DFA construction and figure out exactly which NFA states end up getting grouped in sets that become DFA states. Okay, so all right, I promised an example, so let me do an example. So questions before I start erasing stuff and doing the example. Okay, so hopefully, anyway, some people like the general stuff, some people understand examples better, so we're going to have both. Okay, all right, so we'll do a grammar here. So let's see. So I've got S prime goes to S $, and S goes to A, and S goes to E equals E, and E goes to E. No, E goes to not E. E goes to A. Okay, and so you might recognize this grammar. This is the grammar we had last week, right? So on Wednesday we had an example with this grammar. We had A could be a statement or A could be an expression, and you could assign an expression to another expression. Just to make the example a little bit more interesting, I'm going to add one more production rule, and I'm going to write it as E goes to star E, because I don't know. You can say that the motivation is say like the dereference operator in C, right? So you can take an expression and dereference it with the star. Okay, but I mean, really, it's just an example, right? Okay, so if that's my grammar, now I need to create the LR1. Well, the LR0 DFA and the LR1 DFA, and to do that, I need to do the NFAs first. I'm kind of gonna go faster and go directly to the LR1 DFA, right? And so if I was doing the LR1 NFA, I would start by putting a dot in the start rule as an NFA state. And then because I have a dot before S, I would have epsilon transitions to all the rules that expand S with a dot at the beginning, right? So because there's the dot in front of the S, I would have epsilon transitions to this rule with the dot at the beginning and this other rule with the dot at the beginning. And because this is an LR1, NFA, and DFA, I need to put a look-ahead symbol on these states. And the look-ahead symbol would be the thing that comes after the S here, which is the $. So my epsilon would go to this state and this state in the NFA. All right, so even if you don't care about LALR1, you can still use this as yet another example of me doing one of these LR1 NFA and DFA constructions kind of all in one step. And if you have questions, do ask. I don't see anyone in the chat. hopefully there's people actually there, but definitely if you have questions, ask. Okay, so I would have epsilon transitions from here to here and here in my LR1 NFA. And so these three are going to get grouped together in the DFA start state. And then I also have a dot before an E, and that's another non-terminal. So from this NFA state, I would have epsilon transitions to these other two NFA states. And so I need to put dots at the beginning, and I need a look-ahead symbol. All right, so what's the look-ahead symbol going to be? So the dot is before the E, and then there's an equal. So the look-ahead symbol is equal. And here also the look-ahead symbol is equal. All right, so if okay, and I got some thumbs up, so hopefully that means there's people here, and I haven't messed up the example yet, so good. So now I have, this is going to be my start DFA state, okay? So just in case you're wondering, it's not always the case that, for any grammar that's starting DFA state has all the production rules of the grammar. It does tend to be the case for, small examples that you do in a lecture, but it's definitely not the case in general. Okay, and this is my start state, so I need an arrow pointing into it. Okay, and all right, so let's build the rest of this this NFA and DFA. So the rule is the dot jumps over things, right? So if I have if I see an S, then the dot is going to jump over the S, and I'll have S dot $sign as a state, and then the dot is going to jump over the $sign. So I'll have, and now I need to erase stuff. All right, there we go. Okay, so the dot is going to jump over the $sign. Okay, and then it's over here. And similarly for this rule, if I see an A, and I'm going to just make it a big long transition way out here, just to save space, then the dot is going to jump over the A. Right? And then I have A dot $sign. Okay. Oh, except that's not right. So anyone see why that's not right? Well, here the dot jumps over the A, so that's good. So this would be the correct NFA state. But if I'm in this DFA state and I see an A, what which other ones of these NFA states is going to jump over? Well, in this state, the dot is also jumping over the A. So from this NFA state, if I see an A, I'm going to go to a DFA state that has the E with the dot over the A. Okay, oops, that's not 8, that's the $sign. All right. Okay, and if this is confusing, you can go and as an exercise, draw the NFA first, and then turn that NFA into a DFA, and hopefully you'll get the same DFA that I have. Okay, so we've got the dot jumping over the S, we've got the dot jump over the A, and then I guess the other two are the dot jumps over the E and over the star. Okay, and now I got to figure out. All right, well, let me do the star first. So the dot jumps over the star, okay? So let's put a transition on a star. All right, and so on a star, so what happens? So the dot is going to jump over the star, right? So we'll have E goes to star dot E with an equal sign as look ahead. All right, now, is that my entire state? Well, I don't want to mess up like I did here, so I have to check, are there other stars here? No, no other stars, so maybe I'm done, but no. Okay, why $sign instead of equals? Because I messed up. That's asking about this, I assume. Yes, that should be equals. You're right. Thank you, Yashin. Yes, you're paying attention. Great, thank you. Right, so here, this state had an equals, and the dot jumps over the A, so it should be equals here. Okay, and it's $sign for that one because that state had a $sign. All right, yes, so thanks for that correction. Okay, here it's an equals because there's an equals here. Now, am I done? No, I'm not, because here I have a dot before a non-terminal, so I'm going to end up with epsilon transitions out of that non-terminal, right? So I'm going to have to put in the two rules that expand an E with a dot at the beginning. So E goes to dot A, and okay, and what's the look ahead for here? Well, it's whatever is after the E here, and there's nothing after it, so I take the look ahead. So this is going to be equals, and then I have E goes to dot dot star E. And also with the equals look ahead. All right. So I have a state that looks like this. And I guess while I'm at it, let me see. Okay. So, what else? What else do I need here? Well, now I have a dot before an E, a dot before an A, and a dot before a star. Okay, so I need transitions out on those things. So what one do I do first? Okay, well, what about the star? So if I have the dot before the star, then the dot is going to jump over the star, and I'm going to have, I'm going to have basically this this same item, and then from this item, I'm going to take epsilon transitions to these two. So if I see a star, I actually want to go back to the same DFA state, right? So the same set of three NFA states. When this dot jumps over this star, I end up here again, and from here, the same epsilon transitions happen. So on a star, I actually just loop back. All right. What about on A and on E? Well, let's do E next. So on an E, I want the dot to jump over the E, right? So I want to go to E goes to star E dot with a look ahead of equals. All right. And here the dot is at the end. So there's no more transitions going out. There's no more epsilon transitions or anything like that. And then the dot can jump over the A. So I need a transition out on an A. And on the A, well, the dot jumps over the A. Right? And then I have an equal sign. Okay, so I mean, in the NFA, I would have one state for with the dot at the end of the A with an equal sign as look ahead. In the DFA, sometimes that state is together with this other state with the S. Sometimes it's all by itself, right? If I'm coming from here, I'm not going to be able to get the S, so I just have that state by itself. So this is what I was saying about, the DFA states are not completely predictably grouping the NFA states. Okay, I've got a bunch more to do, but eventually we'll have the LR1 DFA. Okay, so what else can happen? The dot jumps over this E, right? So I need a transition on an E, and so if I transition on an E, I've got E dot equals E with a $ as a look ahead, and here this state is all by itself because there's no other E's with dots before them here, and here the dot is before a terminal, so no epsilon transitions either. Okay, so on E, I go here, and from here, the only transition out is on equals. So on equals, I'm going to go to, okay, so the dot jumps over, let me get this a bit higher. So S, so the dot jumps over the equals, so E equals dot E and $. Okay, and now the dot is what am I doing here? So the dot is before an E. That's a non-terminal, and so I need the epsilon transitions to expand it out. Okay. So sorry, let me just write it here. So E equals, no, the dot is here. Okay. I'm just trying to make sure that this is going to fit on my board, right? So, so on an equal sign, I'm going to go here. All right, and then the dot is before the E, so I need to expand it with epsilon transitions. So I go E goes to dot A with the look ahead symbol. Now my look ahead symbol is $, and then E goes to dot star E, also with the look ahead symbol of $. Okay. All right. Now from here, what can happen? Well, kind of like here, I need star A and E. So let's say I see a star. So I'm going to jump the dot over the E. And so I'm going to have E goes to star, sorry, I'm jumping the dot over the star, not over an E. So E goes to star E with a $ as look ahead. Okay, so no one's posting any comments, so that means I haven't made any mistakes. It's really easy to make mistakes when you're copying these things out. Okay, and then the dot E goes to an epsilon that for all the expansions of the E. So that's E goes to dot A, and the look ahead symbol here is $, and E goes to dot star E, and the look ahead symbol is $. Okay. So now I have a state that looks like this. All right, and so this state, it's pretty similar to this other state, right? It has the same production rules with the dots in the same places, but the look ahead symbols are different. So from the point of view of LR1, these two are two separate states because they're not the same, they're different. But if I didn't have the look ahead symbols, if I was just doing LR0, they would be the same state. And so this is the idea that I'm going to merge them in the LA-LR1 construction. But I'm getting a bit ahead of myself, right? So what about, from this state, what happens if I see, say, a star? Well, the dot is going to jump over the star. So I'm going to have this state, and then I'm going to have the epsilon transitions that from this state generate these other two. So if I see a star, I'm going to loop back to to the same DFA state, just like I did up here. Okay, and what else is there? So what else might I see? Well, I might see a E or an A. So let's say I see an A. All right, let's say I see an A. So the dot is going to jump over the A. So I've got E goes to A dot with a $sign. And again, these two states are similar, but they differ in the look-ahead symbol, so they are actually different states. And finally, if I see E, then the dot jumps over the $sign. Nope, the dot jumps over the E. And what do I get? So E goes to star E dot with the $sign as the look-ahead symbol. Okay. All right. And now I'm not quite done, because in this state, if I see an A, what would happen? Well, the dot would jump over the A. I would go to E goes to A dot with a $sign as look ahead, and I already have that state. So from here, I actually go down to out to this state on an A. And the other thing that can happen here, I had a transition out on a star, but I also can transition on an E. And on an E, I go to a new state, which is S. Well, the dot jumps over the E, right? So S goes to E equals E dot. Okay, and a $sign. All right, so this guy goes all the way over here. Okay, so I think I'm done with the LR1 DFA for this grammar. And, it's a tiny little grammar, right? 5 rules. But the LR1 DFA is already getting quite large. And, as you add even more rules, they just get really big. I just want to check if I've forgotten any states here. Okay, before I start transforming things. Okay, I guess I can just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13. So I'm supposed to have 13 states. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so I've got 13 states. So hopefully they're the right 13 states. Okay, so here's my LR1 DFA. So any questions about the LR1 DFA before I completely mess it up, right, by trying to turn it into an LR0 DFA? Okay. All right. So now to turn it into an LR0 DFA, what I'm going to do is I'm going to take the states and I'm going to delete all their look-ahead symbols. And then states that are the same except for their look-ahead symbols, I'm going to merge into a single LR0 DFA state, right? Because the LR0 states don't have any look-ahead symbols. But then the look-ahead symbols, I'm going to take them out of the states that I merged together. Okay, so what are some states here that kind of look the same, except for their look-ahead symbol? So I've got these two states that I can merge. Okay, so these two are the same except for their look-ahead symbols. So what I'm going to do is I'm going to get rid of this state, and I'm going to put its look-ahead symbol over here. And then all the edges in and out of the state that I'm deleting, I'm going to make them go to the merged state, right? So here, on an A, you're going to go down to this state instead of to this state that I deleted. Okay, so any other such states that I can merge? Well, I've got these two, right? Similarly, I'm going to make this edge go down here. I'm going to delete this state, and I'm going to have a state here that has, again, two look-ahead symbols, one from the original state and one from the other state that I merged it with. Okay, so I'm creating these states where each of the items has multiple look-ahead symbols, right? It's now a set of look-ahead symbols that say, well, if your next input symbol is any one of these two, then you want to reduce when you're in this state. Okay, and then finally, yes, there's only three states that I'm going to end up merging here. But now I'm into the big and complicated states, right? So I have these two states that are the same except for their look-ahead symbols. So I'm going to delete this one and merge it with this one. So it picks up all the look-ahead symbols. So they're all $ and equals. And I redirect the edges. So this edge now goes here and not to that state. And I need to make sure all the outgoing edges, go the right way. But the looping edge here, I already have there. If I didn't have it, I would have to add such a looping edge. The E, already goes here, and I already have an edge on the E. And the A, I've already redirected to go here, so the edge on the A already goes there. Okay, so now, it looks messy, but I now have the LA-LR DFA for this grammar, right? And the idea is that each of these items now has not a single symbol, but a set of symbols. The ones like this, these are just singleton sets, right? Sets of a single symbol each, because I didn't have any other states to merge these with, but in general, they are sets of states. Okay, so now I have the LA-LR DFA. It has 3 fewer states. In practice, if you had a much bigger grammar, the LA-LR DFA would be significantly smaller than the LR1 DFA. Okay, but the way you use this to parse is, like the LR1 DFA, except that you have a set, and so you want to reduce by, say, a rule like this. If if the look ahead, if the next symbol of the input is any of these symbols in the look ahead set. Okay, and the rules for conflicts are as before. So a reduce conflict would happen if you have multiple rules with the dot at the end with overlapping follow sets. I think that would only happen if you already had a reduce conflict in the LR1 DFA. For shift reduce conflicts, those can happen if you have, well, actually, hang on. Yeah, no, that's not actually true. So you can introduce a new reduce conflict. And I have an example that shows exactly that. So if you have 2 different reductions that have overlapping follow sets, then so non-disjoint follow sets, then you get a reduce conflict. And the overlapping follow sets can occur as part of merging states and merging follow sets. Okay, so I don't know. Does the example help? Is the example, you know, any more understandable than the general construction algorithm? You know, I did say that this is, you know, messy and hard to understand. It's kind of one of these things that's practical. It reduces the number of states, but for most reasonable grammars, if they are LR1, they happen to also be LALR1, and so we just apply it, and we hope that it works out without any conflicts. Okay, and so you know, I just said most grammars, if they're LR1, then they're also LALR1. So you know, most means not all, and so people always wonder, you know, what is that exception, right? When do you have a grammar that is LR1 but is not LALR1? So any questions about this example before I erase it and give you an example that's not LALR1? Okay, well, too late. Okay, so gone is the crazy DFA. So, so LR1, but not LALR1. And you actually have to try hard to find an example that's not LALR1. But here's one. So I have S prime goes to S dollar sign. And then I have these, I'm going to have these 4 rules. So S goes to AEA, and S goes to BEB. But I can also say AFB and BFA. B, okay, and then E goes to little e and F goes to little e. Okay, so how does this grammar work? Well, or you know, what does this grammar do? Well, you know, it generates these words of 3 letters. The first letter is always it can be A or B. The middle letter is always E, and the last letter is again A or B. But the idea is, if the first letter and the last letter are equal, if they're both A's or both B's, then you want to parse that E as an E. And if they're not equal, right, AB or BA, then you want to parse that that middle E as an F. Okay. So I mean, if you say, okay, this is a really weird grammar, like who would ever do this? That's sort of exactly the point, right? This is the kind of thing that is very unusual in practice, and almost all LR1 grammars are actually LALR, but you know, here's one that isn't. Okay, and you know, to see why it isn't, I'm not going to do the entire DFA, but let's say you know, we started to build the DFA, so you know, I would have a dot here, and then that entails epsilon transitions to all of the ways of expanding S with a look ahead $sign on the end. Okay, so I have the look ahead $sign, and this would be my start state. Okay, so this would be the start state of the DFA. And then out of this start state, I have a dot before an A dot before a B, and a dot before the S. So, you know, the S, I'll just put dot, dot, dot. The S goes somewhere. We don't really care. But the A and the B are interesting. So, you know, where does the A take me? Well, it takes me to S goes to A dot E A with a look ahead of $. And it also takes me to A dot F B with a look ahead of $. Okay, and if I do the epsilon transitions here, I get E goes to little e, and here my look ahead is A, right? So the look ahead comes from here after the E is an A. So, oh, and the dot is at the beginning. And then I also get F goes to dot E, and here the look ahead is B. Okay, so I have a state like this. And then, well, okay, and then from the B, I'm going to get a similar state. But down here on an E, this is sort of the interesting part. So on an E, the dot jumps over this E. So I've got E goes to E dot A, and F goes to E dot B. Okay, and so this is not a conflict because, even though I've got two rules with a reduction, right, with the dot at the end, well, if my next input symbol is an A, that means my first symbol was an A, so the A's match, so I want the E to be an E. And if my next input symbol is a B, then my first input symbol was an A, so they don't match, so I want that E in the middle to be an F. Okay, and now, the idea is if I, on the B, I get a rule, or I get a state that looks, pretty much like this one. I'll leave it as an exercise for you to fill in this state, but it's pretty much like this one, except with B's instead of A's. And then this state takes me to a state that looks like this. So E goes to E dot, but this one has a B, and F goes to E dot, and it has an A. Okay, so if I reached this state, then the idea is, well, there was so this is on an E, right? So I saw B, E, and so if I see another B as the next input symbol, then I should reduce the E to an E because the two B's are equal. And if I see an A, then before I saw a B, so the E should be reduced to F because the A and the B are not equal. Okay, so that's the idea. And so again, no conflict because on A, I reduce this way. On B, I reduce this other way. Okay, so this is, I need to build the rest of the DFA, but there in the rest of the DFA, there are no conflicts. So this is an LR1 grammar. And now what happens if I go LALR? Okay, all right, what happens if I go LAR? Well, I want to merge states that differ only in their look-ahead symbols. And so that's these two states. And so I'm going to merge them, right? So LA, LR1 merges these two. And if I go and I merge these two states, now I'm saying, well, if I see an A or a B, I should reduce the E to an E. And if I see an A or a B, I should reduce the E to an F. And so now there's a conflict, right? Because now I, for this one LR0 state, the follow sets for both of these are going to have both A and B. And I kind of lose the information of, did I get to this merged LR0 state following the A here or following the B here, right? I'm forgetting that information if I merge these two states. Okay, so if you want an example of where LALR is not actually as powerful as LR. Here's the example, but it is pretty convoluted, right? It's sort of taking advantage of the fact that you're trying to use that earlier information combined with the later information to decide what to do in between. So this tends not to come up very often in practice, and so that's why LALR is what people really like to use in practice. Okay, so smaller DFAs with almost as few conflicts as LR1. All right, so that's all I have about LALR1 parsing. So now, when people talk to people say, oh yeah, I have this LALR1 parser generator, at least you know what it is, and hopefully you know that you don't want to know what it is, right? Because it is much harder to understand what's actually going on than the various other algorithms. So any questions before I erase this and move on? We're pretty much almost done with parsing entirely and ready to move on to the context-sensitive analysis. So, the next sort of overall block in the compiler, right? In the very first lecture, I gave you this very high-level block diagram of the compiler. Okay, so any questions? Can I erase this? Yes. All right. Okay. All right, maybe. Yeah, whatever. I'll just. Okay, I'll erase the middle, and that way, if you think of questions, we can still. We still have this. Okay. So, one thing that maybe is obvious to some of you, but maybe is not quite obvious, is so we went over all these algorithms, and they parse, they decide whether a word is in the language generated by the grammar, and I've kind of been drawing these little triangles to visualize the parse trees, but how do you actually build the parse tree, right? And I think I said it's pretty easy, and maybe to some of you it's obvious, but let's talk about that explicitly. So in the LR algorithms, we've had a stack of symbols. So and they were stack of symbols. So it's a stack that has terminal symbols and non-terminal symbols on it, and that's the stack that you run the DFA on. So that stack in the parser, we're just going to replace it with a stack of roots of trees. Okay, and so a node of a parse tree has a symbol on it. So we're not really changing the algorithm, because whenever the algorithm would look at the a symbol on this symbol stack, well, now this stack is going to contain trees, or really the roots of trees, and so each root of a tree is, it's a node, and it has a symbol on it. So we're still using the same symbols to make the same decisions in terms of parsing, but we're going to just keep track of not only a symbol on the stack, but an entire subtree, rooted under that symbol. And you might recall that in the algorithm, there's these two lines that say, pop gamma off the stack, and then push A, right? So this is where we have a production rule that says that A goes to gamma, and we're applying that production rule in reverse. and to replace the gamma on the stack with the A, right? And in terms of a derivation, the derivation says, as part of a derivation step, you can take an A and replace it with gamma. So if you're doing the derivation in reverse, you can take the gamma and replace it with A. But the sort of the correspondence between a derivation and a parse tree is that each step in the derivation corresponds to a node within the parse tree. And so what I'm going to do when I pop gamma, gamma is now not just a sequence of symbols, but a sequence of trees. So let me, try to draw that. Right. So gamma is, a sequence of trees, rooted. Let's say in this example, gamma is of length 3. So previously in the algorithms, we were only looking at these symbols at the roots of these trees. But now, because it's a stack of trees, we have these entire trees on here. Okay, and now I'm applying the production rule that says A goes to gamma. So each application of a production rule corresponds to a node in the parse tree. And the symbol on that node is the non-terminal. And then the children of that node are the right-hand side of the production rules. So instead of pushing just A, I'm going to push a node with A in it, whose children are the gamma, the subtrees that I popped off in the previous step, right? So these guys are gamma, and so I just take these subtrees that I popped off the stack, and in the derivation, I'm saying that gamma turns into A. The corresponding thing in the parse tree is having a node with an A on it with those trees as its children. So I am going to push, this entire tree onto the stack instead of just pushing the symbol A. And, as I've kept saying, the root of each tree is the symbol that you would have had. So you would have had the symbol A. So now you have a tree that has the A as its root. So in terms of running the DFA on the stack, you run the DFA on the roots of the trees. Okay, and so this is a way that you can build the tree as the parse tree as you're running that parsing algorithm. I mean, there's other things you could do. You could record the production rule applications, in a list, and then build the tree out of that list. But in terms of building the tree directly, this is how you can do it. So I'm not sure if all of this is clear. So are there questions, or is it just generally unclear in certain ways? So any questions about this? Is everybody happy with this? Okay, so in terms of building the tree. So the key is just that instead of putting symbols on the stack, each symbol is just going to be an entire tree. And, it's really just a pointer to the root node of the tree. So you don't have to be like copying trees or anything, because they just have pointers to the nodes and pointers to their subtrees. So you're not copying trees, but you're putting these references to the root nodes of trees. Okay, so I got one thumbs up, so thanks. So hopefully this makes sense. Okay, so building the parse tree, and I have some other sort of small topics to finish up the whole parsing phase. Okay, and so one thing that people often ask, I guess no one's been going crazy on Piazza asking, hey, what's weeding? Weeding is one of those things where, there's nothing really complicated about it, but it's a weird word, and people wonder what the word means. Okay, so if hopefully everyone has been looking at assignment 1, but if you look at assignment 1, it gives you a whole bunch of conditions that you have to check, right? And so some examples of those, there's a whole list in the assignment, but I've got, a class cannot be both abstract and final, or a method has a body if and only if it is neither abstract nor native, or, and let me write one of these down. So an abstract method cannot be static or final, right? So, okay, so, and, there's a whole list of these, kind of annoying little tidbits, right, of checks that you need to do. So these checks, they are things that you could enforce in the grammar, right? So, for example, I could have a non-terminal method modifiers or method mods, and then, okay, and now I can say, well, okay, so a method can be abstract, or it can be static, or it can be final, or it can be public abstract. Okay, abstract, I'll put, dot, or it can be abstract public. All right, or, whatever. Oh, public static and static public, but not, abstract static, and not abstract final, and not abstract static final. Okay, so I could list out all the combinations of modifiers that I could have and leave out the prohibited combinations. And so I could, if I really wanted to, I could enforce this rule in my grammar. Okay, but my grammar would have this really complicated rule with lots of different alternatives. Okay, and yeah, you could do it all in the grammar, but the grammar would be annoying and messy. And a check like this, it's pretty easy to do in code, right? The reason we use a grammar is that sort of figuring out the overall structure of expressions and sub-expressions is pretty tricky to do in code, and it's easy to get it wrong in code. But checking a condition like this, like, hey, if it's abstract, it better not be static or final, like that's easy in whatever programming language you're doing. Okay, and so checking these things that that you could check in the grammar, but you don't want to, right? Or it's easier to do them in code. That's what weeding is, right? So it's after you've built the parse tree, you do a few more checks on it to get rid of some prohibited things that you didn't want to enforce in the grammar. So I will sort of write that down. So weeding is checking requirements that could be enforced by the grammar but are easier to check in code. Okay, so, and the reason that weeding is part of assignment 1 is that, well, when you're weeding, these requirements, it's sort of up to you to decide, do I want to put this requirement in my grammar, or, do I want to not bother putting it in the grammar because they would make my grammar way more complicated, and I'm just going to have the grammar allow some invalid programs, but I'm going to implement a bunch of checks later on to reject those invalid programs. Okay, so it's up to you to decide what to do in the grammar and what not to do, what to write as code. I think in terms of the list that I actually give you in assignment 1, I think they're, or at least I would use weeding for all of those, and I wouldn't bother trying to enforce them with the grammar, but it's your decision. Okay, some of them you might find are easy enough to just enforce in the grammar, and then you don't have to write, those 5 lines of code or 3 lines of code that are going to perform this check, or maybe it's just 1 line of code. I don't know. Right? So okay, so you build a parse tree, you allow some invalid programs, and then you have a little check or a bunch of little checks to reject them, and that's what weeding is. Okay, so there's nothing, fancy or theoretically complicated about it. It's just doing a bunch of checks. Okay, so questions, comments, anything? Okay, so and then there's one sort of final topic on the parsing stage that I want to, which is also another one of these little topics to finish up before we can do the next phase of the compiler. And so that's abstract syntax trees. Okay, so as you're building your grammar for assignment 1, maybe for debugging it, you're having your parser print out the parse tree somehow, and you might have noticed that your parse trees are really complicated. Right, so let's say I have an expression like 1 times 2 plus 3. Because you're making your grammar unambiguous and enforcing precedence, you might have things like factors and then terms, right? And so every factor is a term and a term. So your parse tree might look something like this, or at least mine looks, something like this, but actually about 5 times worse, just because in Java there are more levels of precedence than just multiplication and addition. So my parse tree for this expression is huge, right? But because you're trying to make the grammar unambiguous and you're trying to make the grammar enforce rules of precedence and associativity, right? Do the multiplication first before the addition. The parse tree is huge. Okay, so a huge parse tree, it's okay. It's going to fit in memory. Okay, but okay, in the rest of the compiler, we're going to spend a lot of time writing code that traverses the parse tree. Okay, over and over again. Whatever we do in the compiler, type checking or name resolution or code generation, we're always going to be traversing the parse tree, and each one of those pieces of code is going to have to say, oh, what happens if I see an expression node? What happens if I see a term node? What happens if I see a factor node? So it needs a case for each one of these. So if I can simplify the parse tree, then I can significantly simplify the entire rest of my compiler. So I super strongly, really, really strongly recommend that you simplify the parse tree. So for example, and so this is called an abstract syntax tree. Okay, and so, or AST for short. And so, it's like a parse tree, but simpler. So And so for this expression, I mean, basically, I want to know, okay, it's an expression, and it has two sub-expressions, right? E plus E, and that's one sub-expression is just 3, and the other sub-expression is, maybe two more sub-expressions, 1 and 2, and then the star. Okay, so if I have a tree like this, it's going to be way easier to deal with in the rest of my compiler. One, because I don't have to traverse deeply down from an expression to a term and factor. It's sort of shallower, but also I only have one case to deal with, like expressions, right? Everything is an expression, and maybe for a real language you have more than just an expression, but you don't have to distinguish expressions and terms and factors. Okay, so the idea is that the abstract syntax tree is like the parse tree, but simpler. And the thing that makes it be able to be simpler is that the grammar can be ambiguous. Oh, it fits. All right. Except I forgot the M. Yeah. All right. So, pretend you had an ambiguous grammar for your language, and you could, if you were allowed to make the grammar ambiguous, you could make a grammar that generates these much simpler trees, right? But I mean, when we were talking about parsing, I kept saying, oh yeah, no, you want to make sure that your grammar is unambiguous, right? So how come now it can be ambiguous? Well, the idea is that we're going to build the AST by recursive traversal of parse tree. Okay, so I'm not going to use an ambiguous grammar to parse things and get my abstract syntax tree directly. I'm going to use the unambiguous grammar, get the parse tree, and then I'm going to have a little recursive function that says, oh, well, if I see, say, an expression that's a term, I just want to return an expression node. And if I see a term that's a factor, well, I just want to return an expression node, or things like that. Okay, so I'm going to have one traversal of the complicated parse tree that's just going to build the AST, and the idea is that the AST gets the structure from the parse tree. Okay, so because I build this AST out of the parse tree, then whatever ambiguities that I've prevented in the parse tree are also going to be prevented in the AST that I get. So in other words, if the parse tree has a sub-expression for multiplication, then because I'm building the AST by recursively traversing the parse tree, the AST is also going to have a sub-expression for multiplication. So the overall structure is going to be like in the parse tree. So, even though the grammar would allow an ambiguous tree to be built, I'm not using a grammar to build the AST. I'm using the precedence and associativity rules that the parse tree already enforced. Okay, but the benefit is a smaller tree, a simpler tree, fewer cases to deal with in the later part of your compiler. Okay, and one other thing. So this this last aspect sort of depends on what programming language you're using to implement your compiler. and maybe it doesn't apply if you're using a highly dynamic language, but if you're using a static language, you should use distinct data types for each AST node, or for each kind of AST node. Okay, so when you're writing the code to represent your parse tree, typically you would have just a node, a node class or a node data type, and then within that, within each node, you would have the symbol, like is it an expression, or is it a term, or is it a factor, or whatever. Okay, the AST. This is going to become your major data structure that you're going to write the rest of your compiler around. So it's useful to, design this carefully to, make the rest of your compiler as easy to write as possible. And typically, you would want to be able to tell whether you have an expression or a statement or a method or, or a class declaration or whatever. So you want to be able to distinguish those things in whatever static type system your implementation language may have. And you want to be able to use the features of your implementation language to figure out what kind of node you have, right? So whether that's pattern matching, if you're using some functional programming language, right? You can ask, do I have an expression? Do I have a statement or whatever? If you're using like an object-oriented language, right, then you might want to have like a subclass hierarchy of the different kinds of AST nodes, and then you can use like a visitor design pattern to figure out what kind of node you're currently visiting in the tree. But using a distinct data type for each kind of AST node helps there. So it's worthwhile to think about the kinds of things that you can find in a tree conceptually, right? Not syntactically, so not expression, term, factor, but conceptually. In my Java program, there are class declarations, there are method declarations. Inside a method declaration, there are statements, and inside statements, there are expressions, and the subtrees of expressions are also expressions. And that kind of a classification, and then design yourself a set of data types to represent that AST node, and design it carefully, because this is what you're going to be working with in your code for the entire rest of your compiler. It's often, it's also common to have, say, some mutable fields in your AST data structures, where your compiler is later going to record various facts. So you can add those fields later as you go, as you have a need to record various things. But the point is, the AST is taking the parse tree from this theoretical concept, right, from grammars and derivations, and just a data structure that the parser kind of automatically produces for you from the grammar, into a data structure that you've designed to make writing the rest of your compiler convenient for you. Okay, and it should have significantly fewer different kinds of nodes to worry about than there are non-terminals in your grammar. In terms of assignments, you can build or design your AST at the end of assignment 1 or at the beginning of assignment 2. I think somewhere in between there is sort of a natural place to introduce an AST. Okay, so that sort of wraps things up for the whole scanning, parsing phase of the compiler. With the next lecture we're going on Wednesday, we're going to go into the context-sensitive analysis. Sorry, so any last questions about, I guess, ASTs or about anything else we looked at today or anything else we've looked at so far? So last call for questions. Okay, 5, 4, 3, 2, 1. Okay, well, all right. So everyone have a good couple of days, and I'll see you on Wednesday, same time, and we will start the context-sensitive analysis phase of the compiler. Okay, bye.